Hi everyone, so this is a video of me trying to explain phase constant. Many of you have been telling me that you have problem understanding phase constant. Well, I can understand it, it's a new concept to you. So this is me trying to explain phase constant. But before I explain phase constant, probably we need to know quite clearly what's the meaning of displacement time graph in SHM actually. Well, you have been drawing motion graph since chapter 2 actually. You draw things moving away from the origin, stay at rest, moving back to the starting point. You have velocity time graph, you have acceleration time graph. Well, it's the same motion graph actually. It's just that this time you are drawing it for a motion that oscillates up and down. Okay, before that there's things speeding up, staying at rest, slowing down, accelerating. Well, now it's a complicated combination of all these things, but the motion that you are describing, it's something that's moving up and down repeatedly, or it's something moving left and right repeatedly. This kind of oscillation, we call it simple harmonic motion. Okay, so to really illustrate, to really visualize the concept of displacement time graph, let's look at one video. Okay, so we are trying to understand what is the displacement time graph representing. And this is an MIT lecture video that I cut out a little bit.
First, I'm going to make you see x as a function of time, and I'm going to do that in the following way. I have here a spray paint can, which is suspended between two springs, and I can oscillate it vertically, which is your x direction, like that. So x changes with time. The time axis I will introduce by pulling on this string when the
Okay, so as you can see just now, there's a spring up here and there's a spring down here, and because of these two springs, stretching and compressing, this spray can here in the middle, it's a spray can for graffiti. The spray can is oscillating up and down, okay, because of the restoring force of the two springs above and below the spray can. So let's continue watch the video.
Spray paint is going to spray. I'm going to pull on that string, and if I can do that at a constant speed, then you get horizontally a time axis, and of course vertically you will get the position of x. So I want you to just see qualitatively what kind of a weird curve x as a function of time is, which then will have to satisfy that differential equation. All right, it's always a messy experiment because the paint is dripping. I will try to get the spray paint going. There we go.
Okay, now the interesting part.
Okay, now I'll pull. All right. Could you give me a hand? Yeah, could you please? I'll cut it here, and then you be very careful because it is messy. Or let it take it out this way. Okay, just walk back. Just walk. Yeah, great. Yeah, hold up the top so that you can see it. Fine. Okay. What does it remind you of?
Well, what does it remind you of? It reminds me very clearly what graph is this. Yes, it's a graph that you have been drawing for your SHM, right? Okay, so it's just an SHM graph. So let's continue to hear what Professor has to say.
Sinusoids. Reminds me of a cosinusoid, by the way. Sinusoid or a cosine, same thing. All right.
Okay, so yes, who is this lecturer? This lecturer is Professor Walter Lewin. Professor Walter Lewin was an MIT lecturer, and he is one of the very important inspirational figure during my time learning physics and also my time teaching physics actually. I'm motivated to do demos in my lectures or in my class mostly because of him. I've been watching his lecture when I was learning physics, And if you have watched his lecture before, there's plenty of demos in his lectures, and all his demos are very useful in making students understand things. And yes, that's one of the goals that I wish to pursue in teaching. That's why I always try to include demos in my teaching. So if you are happy with having demos in class, that's Professor Walter Lewin from MIT that you need to be thankful with. Okay, so let's review a bit of his video and unpack some of his stuff. Okay, so let's watch it from the start.
First, I'm going to make you see the function of time, and I'm going to do that in the following way. I have here a spray paint suspended between two springs, and I can oscillate it vertically, which is your x direction, like that.
Okay, so when the thing is oscillating, originally it has a position where the spring is not compressed, the spring is not stretched, the string is just in its position, like its neutral position, you can see. Okay, so that's that point. Okay, I'm using the bar as a reference. That point here, we can call it the equilibrium point. Okay, so
X changes with time.
oops.
The time axis I will
Should draw it here. But when it's at equilibrium, when it's fluctuating between the highest point and the lowest point, you can see that there's a fixed highest point and there's a fixed lowest point. Okay, so that's how the thing oscillates in between. So it goes up and down, up and down, up and down, and up repeatedly. So we represent this height here from the equilibrium to the highest point, this one as amplitude. Okay, then as time passes, the spray can will be at different position as time passes. Sometimes it's at here, sometimes it move up, it move up, it move up, it move up, it move down, it move down, it move down, it move down. So at different time, the position is different. So what you see on the graph paper later, it's a representation of the position of the spray can at different time actually. Okay, so
introduce by pulling on this string, and of course vertically, which then will have to satisfy that differential. Try to get the spray paint going. There we go. Okay.
Okay, so at this point, when he's not pulling the paper, the spray can is constantly spraying at one position like this. So this is what normal simple harmonic motion you see, you observe from a simple harmonic motion. It's just oscillating like this or oscillating like this, nothing special. But the moment you try to pull it against time, means by the moment you start pulling it, then you see the sinusoidal pattern.
Now pull. All right.
Okay, so Professor Walter Lewin pulled it with a constant velocity. That's why the sinusoidal graph looks really nice. So the pulling action means like you are recording it as time passes. It's like a recording as time passes. So when you take out the thing, then that's where you see.
Could you give me a hand? Yeah, could you please? I'll cut it here, and then you be very careful because it is messy. Or let's take it out this way. Okay, just walk back. Just walk. Yeah,
Professor Walter Lewin is fun. If you notice, he's putting a banana on his shirt.
Fine.
Okay.
Okay.
Do you see the banana?
What does it remind you of?
Okay, so well, it's a displacement time graph. So my best ability to draw this graph would be something like this. So this will be the displacement in meter, then this will be the time in second. So basically this is just a displacement time graph. This is still the best way for me to imagine how a displacement time graph represents. It presents a change in position of the oscillating body as time passes. Okay, so if you see here, it looks similar to a cosine graph. Okay, but in your syllabus, what you learn is probably the sine graph, which probably looks something like this. Okay, so this is a sine omega t graph. What you learn, there's no phase constant in your syllabus. So this is what you learn in your syllabus. And as you can see, it starts from the equilibrium position. It starts here. Okay, this position here is called the equilibrium position. Not the one that I circle. I shouldn't be vague about this. Equilibrium position is the whole x-axis here, is the equilibrium position. Okay, so the thing move away from the equilibrium position, come back towards the equilibrium position, move away from the equilibrium position, move towards the equilibrium position. It's constantly moving away and toward, away and toward, away and toward the equilibrium position. This is what we call an oscillation. It oscillates around an equilibrium position. Simple harmonic motion. Okay, but it's not a must for your stuff to start, your oscillating things to start from the equilibrium position. You can start from the maximum point, maybe. Okay, you can start from the maximum point or the maximum displacement. You can imagine it as having a slinky spring. Okay, so the graph above will be something like this. Okay, it starts from the equilibrium position. Okay, whereas for the cosine graph, it will be something like pull it to the amplitude, or you put it to amplitude. This one is above. Put it to amplitude, then you let go, then you let the thing oscillate. Okay, you can think of it like that. Let me hilangkan the webcam first. Then this is a sine omega t graph and a cos omega t graph. So this one starts from the highest point. It starts from the amplitude. You can also start from the negative amplitude. Means I start from the lowest point. It means by you stretch the thing first, then you let go, and let it oscillate. Then there will be a negative a cosine graph. There's many ways to draw the graph. Even there's negative a sine omega t graph. Just that the thing starting by, it is an negative a sine omega t graph. It starts with going downwards, then come back up, then coming up, going downwards. Okay, so depending on how the thing starts oscillates, then you have different representation of sinusoidal curve. Okay, there's negative a sine, there's a sine, there's negative a cos, there's a cos. But these are still very specific cases. You might have your graphs, you might start somewhere not at the amplitude, you might start somewhere not at the equilibrium position. You might have a graph that looks something like this. Okay, it starts not at the equilibrium. It starts not not at the maximum point. So in that case, right, you need to have a more general equation. You need to have a more general equation. So a more general equation is needed. Okay, so since you want a more general equation, So now I give you the more general equation. The more general equation will be x equals to a sine bracket omega t plus phi, okay, or x equals to a cos bracket omega t plus phi, okay. So either one of them, you can just take it and use it. Because our syllabus using sine, so maybe a sine omega t plus phi is what we will be usually using. Okay, doesn't mean but you need both to be general. Only one of it will be enough. Okay, you can represent any a cos graph with an a sine graph. Okay, you don't need both, you just need one, but both are usable. Okay, so we will be using this graph. So this graph, this is still the same thing, still the same thing, still the same thing, still the same thing. This one is the new thing, which we call it as initial phase constant. Okay, initial here means by it's, we have this thing because of our start is different. Okay, if we all start from the equilibrium, then we don't need to have phi. Okay, if we all start from the maximum displacement, we don't need to have phi. I mean, you can still have phi. I mean, it's complicated, but the real, I mean, the most useful purpose of phi is to represent general situation where you start differently. Okay, so phase means by phase is a very abstract concept, but you can think of phase is like which section of the wave, which section of the sinusoidal curve. Okay, if it's a sinusoidal curve, you can think of you are at this particular phase, or you can think of it as you are at this particular phase. Okay, which section or at which point of the sinusoidal curve are you at? You can call that thing phase. So this whole thing is 2 pi radian, right? It takes one full oscillation is 2 pi radian. So in that case, let's say we can split it into 4, then I must have very bad eyesight. If you split into 4, then this one will be pi over 2. So means by the distance, the phase difference is pi over 2. Okay, it's a complicated concept. It's really difficult to explain. But it means by how which section of the sinusoidal curve you are at. Okay, then constant means by it's a constant because the way you start it, that's the way you start it. You can't change the way you start the oscillation in the middle of the oscillation. That's why it's a constant. You won't change its value unless you restart the experiment. You have new t equals to 0. You have a new start at t equals to 0. Then your phase constant change. But in the middle of an oscillation, the phase won't change. Okay, so this is the equation x equals to a sine omega t plus phi. So let's try and graphically try to represent this thing. So to represent this thing, I'll move on to a software called Desmos. So let's move. Oh, before I move on to Desmos, here's one thing I wish to correct. If you look over here, I have changed a bit of my graph. The starting, even if you are not starting from the maximum point or you're not starting from the equilibrium, you shouldn't draw it like how I draw it. How I draw it last time is I curve downwards, then I go up like this. It shouldn't have this kind of features. It should feel like a sinusoidal curve being chopped in the middle. Okay, so you shouldn't have curve that looks something like this. Okay, just a little thing, a little mistake that I made. Please take note. Thank you.